All right, so this is the Continental Drift PowerPoint. Again, it starts with a few quiz questions on earthquakes, so go ahead and give those a shot and let me know if you have any questions. I typically start this off with an activity that I developed over time. I basically give students a jigsaw puzzle, an actual jigsaw puzzle that I get from the dollar store. I've cut some of the pieces off of the ends of the puzzle so that they don't fit together very well. And I have them try to reconstruct the puzzle with the cardboard side up. And that's sort of how I start this. It's a frustrating activity, and students can't usually solve the puzzle, even though it's a smaller number of pieces, maybe 25. Um, and the reason I do that is to get at this question of how increasing levels of evidence provide more help in reconstructing the puzzle to get at the evidence that we have for continental drift. And so that's how I typically start this if we were meeting in class, and give you about 5 minutes to do that. Like at the end, you probably would find out that you can't do it. And some of the reasons that people get is that the puzzles pieces don't fit together very well. So if we had the actual pieces that fit together well, that would help. The color scheme that we can see on the other side helps, looking for patterns. If we knew, for example, that we were looking at an eyeball, we could look for other pieces that had an eyeball on it and put that puzzle together that way. So carrying that idea over onto continental drift, then the idea of continental drift is that in the past the continents were not always located where they are presently located. And so that's the main idea. We'll talk about plate tectonics in the next PowerPoint. The main difference between the two is continental drift doesn't describe how this happens. The idea was simply that the continents seem to have been at a different place in the past. It was proposed somewhere around 1912. See, he did some work leading up to this, but by Alfred Wegener. I tell you he's German because it's pronounced Wegener, not Wegener. He was more of a meteorologist than a geologist, and so not taken real seriously, but taken seriously enough that people tried to, other scientists tried to discredit this notion. And in doing so, they really found additional evidence that supported the idea that maybe the continents had been in a different place in the past. And so what Wegener first noticed is that some of the continents, even today, if we cut the continents out of a map, put them together, Africa and South America fit together really well. And so he thought maybe this was more than a coincidence, and started to do some research trying to match up rock layers and such, and found that maybe there's something to this. He wasn't taken very seriously, so other people tried to find some disconfirming evidence, and in doing that they couldn't, which again strengthened the theory. So there's multiple lines of evidence. This idea of Africa and South America fitting together well could be a coincidence, right? We have this coincidence that the moon in an eclipse is just the right size to cover up the sun. So that's a coincidence. So any one of these could be a coincidence. We see it fits very well, but could be a coincidence. So the idea here is that if Pangaea existed, so Pangaea being that sort of supercontinent that existed in the past, if it existed, then obviously the continents have moved, and therefore continental drift is a supported theory. So Pangaea, surrounded by a large ocean, depending on your preference there, we call that Panthalassa or Panthalassa. And important to note that there were continents in different places before Pangaea. They came together to form Pangaea, and about 200 million years ago began breaking up into smaller continents. It's just that the further we go back in time, the more difficult it is to reconstruct what happened before Pangaea. But do note that the continents existed before Pangaea. This is not the start of the movement of continents. This is just what I thought was an interesting picture. If we look at the current location of different countries, where they were in Pangaea time. All right, and so here's sort of the breakup of Pangaea over time, going through the Permian, Triassic, Jurassic, Cretaceous, and the present day. There's also some graphics that project into the future where the continents will be. All right, so multiple lines of evidence coming together, just like we need multiple lines of evidence to put a jigsaw puzzle together. So the first line of evidence was the pieces fit together, the continents. The second was identical fossil remains found in two adjoining parts of Pangaea. The example usually used here are things that really we don't think would do a good job of swimming across a large ocean. And so there's a couple examples. Mesosaurus is one used by a lot of textbooks. We'll look at a picture of that on the next slide. The second is the age and type of rock. So we've looked at stratigraphy, or layers of rock, those matching up in the same sequence, the same order, in two places that are now separated by a large ocean. So that's evidence 2 and 3. And here's the spread of fossils. So these different color bands are the only places that we find these particular fossil remains. I realize that's hard to read, but the green is the Mesosaurus, and that's the only place that we see that. So again, it could be a coincidence, but those patterns seem to match up pretty good for a lot of different fossils. All right, and then the, I guess, fourth line of evidence are coal deposits. Now this isn't rocks matching up. Coal, if you recall, one of the ways that coal forms is in boggy kind of swamp-like environments. And so if we look at where we mine coal today, these are not in boggy swamp-like environments, right? We don't think swamps when we think about Ohio and Pennsylvania or Siberia. And so the idea is that for these coal deposits to form in these locations, they had to be closer to the equator, where we presently find warmer swamp-like environments. And similar to that, glaciers really tell us two things. When glaciers move, they scour the earth with large rocks, and so we can get an idea of the direction that the glaciers were moving, but also where they are located. And so we see that here. For these glaciers to exist, they would be a shift closer to, in this case, the South Pole, further away from the equator. The arrows also show that if Pangaea was not together, the glaciers would have been moving from water up onto land or uphill against gravity, and we know that that can't happen. And so the only way to describe that is through Pangaea, that it was one landmass. You can see some other lines of evidence up in the top, but I won't go into detail there. So there are these multiple lines of evidence that all add up to indicate that the continents have moved in the past, and Pangaea was once shifted, all the continents together, but shifted closer to the south. The next activity I'd like you to do is sort of pause here and do this activity that's in the lab manual. It's on pages 52. So as you start with Lee Redmond here, she was a Guinness Book of World Records holder. I had for quite a while, many years, been telling students that plates move at about the rate that your fingernails grow, and a lot of textbooks say that. So here's an example of that. So I figure we might as well just calculate the rate that fingernails grow. Since Lee Redmond's in the Guinness Book of World Records, we can do that. And so that's what that sheet is about. If you take a minute to calculate that, you'll get the rate of Lee's fingernail growth. All right, so after you get the rate of Lee's fingernails growth, we know that, but we're really interested in the rate that continents move. And there's a couple of different ways that we can calculate that. We need the same information we would for Lee's fingernails, right? We need the distance and we need time. And so you had the distance or the length of the fingernails and the time that she grew her fingernails. And so if we can get that data, we can determine the rate that a plate moves. We can do that with hotspot volcanoes. And so the Hawaiian Islands are an example of this, and that's our next activity on pages 53 and 54. I'm going to skip through this, but these are islands that form over a hotspot or a magma chamber that is stationary and doesn't move. And for that reason, you can see that it creates a series of volcanic islands that are shield volcanoes. We know the age because that lava cools, and we can date the age of it using radioactive dating, right? And we know the distance between the islands. So we have distance and we have age. And so we can calculate the rate of plate movement. So again, you can pause there for a minute and do pages 53 and 54, and then we can really sort of compare those numbers. All right, so after you compare the numbers, you see that from the activity, those numbers that we get don't entirely match up with Lee's fingernail growth, but this picture shows the rate of plate movement in different areas, and you can see that they vary widely. Some are moving rather fast, and some are moving very slow. So here's one at 2.0 compared to a very fast-moving 18.3. So there's some variety, but Lee's fingernails and the Hawaiian Islands data that we get fit in here, and so I do think it's a fairly accurate representation. But it is a representation, so fingernails aren't plates moving, but it is something that we can calculate. There's some accurate parts of that and some inaccurate parts, but overall I think saying that plates move at about the rate that fingernails grow is something that we can help students understand, but also keeping in mind that our individual fingers probably grow at different speeds and vary from person to person, just the way that plates vary. All right, and then the last thing we can do is determine the direction that the plate is moving, and to do that you really have to understand how hotspot volcanoes form. So I'm not going to click on this YouTube here, but I'll just try to describe what you see if you move to the 8-minute and 48-second. So if you think of Hershey Kisses, there's a little nozzle. That nozzle squirts out a little bit of chocolate onto this conveyor belt, and then that conveyor belt moves away from the nozzle. So that nozzle is stationary. It doesn't move, right? That's your hotspot magma chamber, right? It doesn't move, but the Hershey Kisses move away from that. And as they move away from the nozzle, they're cooling down to form, the chocolate that we can put a wrapper on. And that's very similar to what's happening in these hotspot locations. This plume is stationary in a layer called the asthenosphere. On top of that, the lithosphere is moving, and it's forming these volcanic islands. And as they move away from the magma chamber, they're no longer active. Right? They get progressively older, and to the point where they're so old, they become seamounts, and that's what we saw in that original picture of the long sequence. Seamount basically is when the ocean starts to weather the material so much that it's no longer above it's no longer an island above the water, it's beneath the water. All right, so that's how we can determine the direction, right? Each of these volcanic islands, Kauai, Oahe, Molokai, Maui, so for example, Maui used to be located over this magma plume. It has since moved off in this direction, and so we know the direction of plate movement. Okay, so the way we do that is look at the oldest. We know that it was once where the youngest is. We know the youngest is currently active, and so it's above the plume, and it's moved away from that plume. So that gives us the direction. Here you can see it's to the northwest, and you can get that from your top-down image, going back to that picture here as well, right, off to the northwest. So this was once located here and has moved off to the northwest. All right, so hotspot volcanoes are one of the ways that we can determine the rate and speed that, the rate and speed are the same thing, the rate and direction of plate movements. And so we'll look at another way in the next PowerPoint that we can also determine the same thing, the rate and direction of plate movement. But this is one way. I think it's a pretty easy way to demonstrate that with the students that you'll be working with. All right, so I'm going to stop there. The next activity we'll get to will be plate tectonics. So for this, there's the building Pangea, Gizmo, you did the fingernail growth activity, and the rate of crustal speed lab. Okay, so we can discuss those on Tuesday. If you have any questions, feel free to email me.